the last class, we talked about the JK flip-flop, applied it as a counter, a ripple counter. So let's take a relook at that ripple counter. So basically what we did was we had 4 of these flip-flops, okay? And the clock, the master clock, was only connected to the first flip-flop, right? So these are the J and K. Again, just to recall what the J and K, how the J and K works. So that's your JK flip-flop characteristic table. That's your QT plus 1. That means if I apply as input 0, 0, in the present instance, in the next clock transition, I'll get an output of, well, basically it's Q of T. Basically, that corresponds to the memory condition. 0, 1 corresponded to the reset condition. 1, 0 was the set. 1, 1 was the toggle state. And we applied this toggle state in the design of the counter, right? So we call that JD, KD, JA, JC, KC, JB, KB, and JA, KA. The way we designed the counter, again, we assume that we have designed them using these negative edge triggered flip-flops. We configured each of the flip-flop in the toggle state. That means the output toggles with every clock pulse, every new clock pulse, the output toggles. Okay, goes from 1 to 0, 0 to 1 with every clock pulse. We know what the toggle state is. And so basically we configured each of the flip-flops in the toggle state by applying a 1 on my J and K values. So that's why I get, with every new clock pulse, I get the toggled value of the previous output value. The master clock was applied only to the first flip-flop. And for the subsequent flip-flops, the output of the previous flip-flop is applied as the input as the clock signal of the next flip-flop, right? That's QC, that's QB, and so on, right? And that's why we call this the ripple counter, because the clock ripples through, the effect of the clock ripples through these stages, through this configuration, right? And it worked well. We didn't see any particular problems. We derived we examined this circuit by using the timing diagram for this circuit, and everything looks fine so far, right? Now, but there are issues with this, and that's what we want to talk about in this class today, okay? At least in the first few minutes of this class, let's talk about what could be potential issues here when we're trying to use this. Again, going back to our previous examples, right? Now, if I want to build a 5 or a modulo 32 counter, what do I have to do here? 32 counter. How should I modify the circuit so I can build a modulo? Again, remember that modulo 16, that the number 16 or this number corresponds to the number of unique counts you would have. For example, this particular circuit is a modulo 16 counter. That's absolutely right. I basically add one more flip-flop, right? And then basically take the output of this flip-flop and as the input to the next flip-flop, configure that flip-flop as in the toggle state, and then I get a modulo 32 counter, right? So right now I have a modulo 16 counter. So that way I can basically add new flip-flops and I can get a larger count. Basically I can enlarge the size of my counter simply by adding new flip-flop stages, right? So that's kind of understandable from here. Now, can I do that indefinitely, or would I be landing into a problem? Right, that's an issue, right? That we need to address. What do you think? Can I just keep adding these additional flip-flop stages and get a large counter? Because again, remember that, and in the last class we discussed about this. Now, your current clock speeds for your computers, these are in the gigahertz range, and if I want to show the clock, the time on there, which shows your hours, your minutes and seconds, I need to really frequency divide that original clock speed so that I can actually get these periodic signals that correspond to your hours, your seconds and minutes. Right? So that means I need to have multiple, if I want to build this using this concept, I need to have multiple flip-flop stages so I can divide this by a large amount. Right? I can frequency divide the original clock period by a large extent. Okay. Now the question is, would I land into any problem if I just keep on adding stages? If I want to build a large counter with n, a delay will be issued. So as you guessed, yes, there will be a delay. But what kind of a delay? Where would the delay come into picture here? In digital circuits, when we talk about delays, again, these correspond to always the the uh, the switching speeds, right? How fast the circuits switch from one value to the next, right? Now we can actually examine the problem by again taking the truth table, taking the timing diagram of the circuit again. If I want to draw this and illustrate that actual effect of the delay, let's actually look at the timing diagram because that will tell us the entire picture. Again, because the clock, I want to reference everything with the master clock. So that's my master clock that I draw as the first signal, and then reference everything with the master clock. Okay. Now, this is again, these are negative edge triggered flip-flops. So that means I need to identify the active edges. So these are my active edges in this case. If I want to draw QD, that's my clock. If I want to draw QD, what would that be? As you can see here, right? Now, because I've configured this D flip-flop or JD KD flip-flop in the toggle state, my QD has to toggle with each active edge, right? In other words, so these are my active edges. My QD has to toggle at each active edge. Ideally, if there was no delay, then this should basically toggle right here because that's exactly where my clock is going down. That's the active edge. However, because of the finite time delay, it's a very small, because if I'm considering a single flip-flop, the timing delay is going to be very small, right? The switching speed, the timing delay is going to be very small. So, but it is there. It's not like a zero timing delay. So I would still have some finite amount. So instead of switching right here, right, it switches after, let's say, timing delay of, for each flip-flop, on average, let's say the timing delay is TF. Okay, for each flip-flop. That means this is the active edge. My flip-flop, instead of switching right on the active edge, it would switch after a timing delay of TF seconds. Okay, so this particular, I don't know if you are able to see that. So this particular thing, that's my TF. Okay, and likewise, this would switch after a delay of TF seconds. Okay, and so on. Same thing here. It would switch with a delay of TF seconds instead of switching right at the clock edge. All right. Now, what about QC? Now, remember that for QC, my QD is the clock. So this is the clock. And these are the active edges for QC. So if I want to draw QC, again, QC or the JC KC flip-flop will have its own timing delay. And again, because we consider TF to be the average timing delay for each flip-flop, then my QC would be switching with a timing delay of TF with respect to this particular QD. with respect to QD, right? So QC, instead of switching right here, because that would be where you expect the flip-flop to switch, that would switch with a timing delay of TF seconds. So that's TF seconds again. Now, with respect to the master clock, because again, we want to reference everything with respect to the master clock, what is the timing delay for QC? It was supposed to switch here, right? But it's switching here. So that's TF, that is TF. So that means, so this is TF, that's 2T and 2 times TF. Okay, again, that's a good question. How do we decide how much of the delay we should mark? Just assume something for now. It's a very short delay, okay? So just assume a very small value for now, some small value, okay? And we'll see what does that value depend on later on. All right, so that's TF. That means the timing delay of this particular, the switching of the QC with respect to the master clock. If I extend this became 2 times TF. So in other words, as I'm extending the stages, as I'm adding on new flip-flop stages, the timing delay for the nth flip-flop also increases n times, right? Now, what does that have as an effect on my count? Because ultimately, that's going to affect the count. So let's say 0, 0, 0, 0. Again, remember that this is the first flip-flop. That's QD, QC, QB, QA. All right, so that's QA, QB, QC, QD. That's the clock pulses, number of clock pulses. On the 0th clock pulse, that was 0. On the first clock pulse, we see that that's 0, 0, 0, 1. I don't have to worry too much about the QD timing delay because it's supposed to be very small. Okay. On 2, supposed to become 0, 0, 0, 0, 0, 1, 0. So with every clock pulse, my QD toggles, which is fine. Okay. Now the problem is, what if for a particular stage I have a situation something like this? Okay, let me actually take this out and then look at this again. Now I have this clock pulse, the master clock pulse. These are my active edges. And for a particular stage, I have added n stages. And then for a particular stage of the flip-flop, it's because the timing delay adds up with each added stage. My flip-flop timing delay is increased so much that instead of switching here, it starts switching here. The delay has added so much. Let's say that's n times TF. This is the active edge where it was supposed to switch. It is switching here, okay, which is still okay as long as it's not switching on the next active edge. Because let's say this is QB. This corresponds to QB. Let's say in this example. So in this case, 0, 0. I have 1, 1. On the 4th clock pulse, it was supposed to switch and form this, right, and get the count like this. Now it will still get the count with a slight delay, which is fine for 1 clock pulse, which is fine as long as my n times TF is less than the clock period of the clock. This is my clock period TC. As long as n times TF is less than TC, I'm okay. So switch still, I would still get the right count, even if it's small with a small delay, which is fine. The moment it exceeds that, if I have a situation where, for example, here, so instead of switching here, I have timing delay added up so much that it starts switching on the next active edge. Now that's the problem, right? Because now on the fourth clock pulse, instead of getting this value, I'll be getting basically 0, 0, 0, 0. And on the fifth clock pulse, I will be basically getting 0, 1, 0, 0. That means I have an intermediate value, intermediate count that is not what we want, right? So for one clock pulse, I would basically have this count, which is an invalid count, right? So I need to, so for this particular flip-flop to work, I need to limit the number of stages I need to use. Limit the number of stages so that my n times tf, whatever the tf is, something in the nanoseconds, but it gets added up. If I have very large number of stages, I need to make sure that n times tf is less than tc, the clock period. Otherwise, I would be ending up with getting some intermittent wrong counts as a count value. Okay, so that's important. Or alternatively, I design my clock signal to have a large TC value, which is not desirable, right? Because we want our circuits, we want my systems to work fast. I would like to work with a faster clock. I don't want to slow down my clock, in which basically slow down my entire system, right? So obviously, so we have identified a problem, a limitation of using a ripple counter, okay? And you can, in a way, this is called an asynchronous counter because, except for the first flip-flop, the rest of the flip-flops are not really synchronized with the clock. You have some desynchronization happening with the master clock because of the timing delay. So this is also called an asynchronous counter. Okay. All right. So how do we? So this is a very important example or an illustration of what happens when you don't synchronize each of your circuit elements with the master clock, or if you introduce components in the path of the clock. You don't want to do that, right? This is exactly what's happening here. We have introduced components in the path of the clock instead of synchronizing each of my stage with the master clock, right? I am having some components that are applied in the path of the clock through this arrangement. Okay, so that's something that we need to avoid when you're trying to design these kind of circuits, because this clock is the one that is synchronizing all of your units in your system, and we want to make sure that each of the unit is powered by the master clock, so that everything stays synchronized with the master clock. Okay, so now that leads us to how do we address this problem, and basically that leads us to a new design of the counter, and we call that the synchronous counter design. So this is an asynchronous counter. Let's look at the design of a synchronous counter, how that works. Okay, a synchronous counter. So the idea is you don't want to introduce anything in the path of the clock. So in this case, we would still use the JK flip-flop, and I would keep the characteristic table handy here. That will help us in the design of this JK flip-flop. Okay, and that goes something like this. So you have J, K, Q, T plus 1, 0, 0, 0, 1, 1, 0, 1, 1. That's memory, or Q of T. That's 0, 1, Q prime of T, or toggle state. Okay, so this is what we had, and let's design a 4-bit counter. Okay, again, I will use my JK flip-flops for this. I'll use 4 of those. So these are the 4 flip-flops. Okay, let me call this JD, KD, QD, JC, KC, QC, JB, KB, QB, and JA, KA, and QA. Okay. Again, let's start with these negative edge triggered flip-flops. All right. Now, because I want this to be synchronized with the master clock, right? That's why we call this the synchronous counter. I start with ensuring that each of my flip-flop stage is driven by the master clock. And then I can do any modifications or additions to the circuit to make it work according to the specifications. So that's the clock applied to each of my flip-flop stage. So I don't have to worry about desynchronization here anymore. Okay. So each of the flip-flop stage is applied to the master clock. So that's every stage is synchronized with the master clock. So that's good. Now the way we would design this, let's go step by step. Let's look at what we want to achieve here. What kind of a pattern do we want to achieve? And then we'll go about designing how to obtain each of the pattern. For example, here, so let me call this is the clock, the number of clock pulses. Let me call that QA, QB, QC, QD. On the 0th clock pulse, everything is 0, which is fine. On the first clock pulse, I have 0, 0, 0, 1. Second, 0, 0, 1, 0. Third, 0, 1, 0, 0, 1, 1. Fourth, 0, 1, 0, 0. On the fifth clock pulse, I will have 0, 1, 0, 1. Sixth clock pulse, I should have 0, 1, 1, 0. Seventh, 0, 1, 1, 1. Eighth, 1, 0, 0, 0. Ninth, and so on. Okay. So that's the count pattern I should be getting for this particular circuit. And now let's examine each of the outputs separately and see how would I get to obtain the pattern. So let's start with QD. That means what should I configure this particular flip-flop so that I can get QD output? Any ideas here? So that my output QD should toggle with each clock pulse, with the master clock pulse. Again, this is the master. I'm referring everything to the master clock, right? So what should I configure? How do I configure the first JD-KD flip-flop as to get the QD output with each clock pulse? What should I do here? I'm trying to obtain the outputs of this flip-flops independently. So first I examine QD. QD goes as 0, 1, 0, 1, 0, 1, 0, 1. That pattern with respect to the clock with each active edge that goes as 0 with each active edge is basically toggles. So what should I do for QD to obtain QD? Any ideas from the class? Let's make it a collaborative effort here to design that synchronous counter. That will be more fun. It's actually a fun circuit if you work that way. Kim, do you have any suggestions? David? Okay, J equals K equals 1. That's it. I can, by applying J equals K equals 1, I configure this as a toggle flip-flop, and it will toggle with each clock pulse. But again, remember that the clock is applied, the master clock is applied to the flip-flop directly. So just by configuring this as a toggle flip-flop with J equals K equals 1, I get this output. So that's good. So I got this figured out. What about QC? How do I get QC? It should also toggle, but in a different way, slightly different way compared to QD, right? I cannot apply QD as a clock anymore because again, that would transform that into a ripple counter. I want to come away from the ripple counter. I want to get the synchronous counter here. Now let's examine QC in more close detail. Okay, so QC is 0 on the 0th clock pulse. QD is 0 on the first clock pulse. QC remains 0, kind of like a memory. It's retaining the value of the previous state of the previous clock pulse. It's retaining that value. QD becomes 1. because the way we have configured it. On the third clock pulse, QC toggles. QC toggles, okay. QD becomes 0 because it's continuously toggling. On the fourth clock pulse, on the second clock pulse it toggles. On the third clock pulse, it keeps the value 1 unchanged. That means it's configured in a memory state, right? Because it's keeping the previous value unchanged. Here also the same thing. So we can say from 0 to 0, that was in the memory state. 0 to 1, it toggled. 1 to 1, memory state. 1 to 0, toggled. That means it's kind of oscillating between a memory state for one clock cycle and a toggle state in the next clock cycle. Do you see that for the QC value? So it's oscillating between memory state and toggle state. Okay. Now, how should I configure my JC and KC? I cannot do anything with the clock because that's already applied. How should I configure JC and KC so I can obtain QC behavior with respect to the master clock? Any ideas here that you can think of? Q equals J equals K. What is Q here? Because I have QD, QC, QB, QA. Which Q are you referring to? QD. Okay, let's see if that works. So if I apply QD as a signal to JC and KC, what will happen? Again, you go back here. QD was 0. This is 0. I'm applying QD as an input to JC and KC on the 0th clock pulse. So in the next active edge, again, remember QT plus 1 corresponds to the next active edge. The next active edge, if I'm applying J and K to be 0, 0, because I'm applying QD of 0, that means JC and KC are 0, 0. In the next active edge, it retains the same value that was there before. So 0 was retained as 0. So that's good. Now, QD value itself changed on the first clock pulse. That became 1. Okay. Now 1 is being applied to JC and KC. All right. And in the next clock pulse, QT plus 1, if I apply 1, that means that refers to the toggle state. So in the next clock pulse, my 0 becomes 1, toggles, right? Because 1 is being applied. And on the third clock pulse, that is at QT plus 1, my JC and KC is configured as a toggle flip-flop. That means my 0 has to toggle to 1. And in the meantime, my QD itself toggled to 0. So I'm applying a 0 again on JC and KC. 0 on JC and KC, right? My present value is 1. I'm applying a 0. So in the next clock instance or the next transition, because it's configured as a memory, it retains the same value. And so on, the behavior continues, right? So in one clock pulse, I'm configuring this flip-flop in the memory state. And in the next clock pulse, I'm configuring this as a toggle state. So it's kind of oscillating between those two stages. So that's good. So that works. That should work. So now I obtained QC by this modification or by this configuration. How about QB? How should I get the QB behavior now? So let's look at QB. So QB has to be 0 for 4 clock pulses, right? And then it toggles. And once it toggles, it needs to remain in the memory state because it's retaining the same value for the next 4 clock pulses. Then it toggles again and retains the same value for the next 4 clock pulses, and so on. So that behavior continues. So how do I configure QB to get that behavior, or the JB and KB to get the QB behavior for my flip-flop? Any ideas here? Okay, so QC equals JB equal to KB. Let's see if that works. QC equals QC times QD, JB, okay. QC is JB. First, let's examine the first one. QC equals JB and KB. Would it work? So QC, so let me just do this. So it's clear. So now I'm applying QC directly on JB and KB. So that's fine. So 0, that configures this as memory. So the next clock pulse, it retains the same value. So that's good. Next clock pulse, it is still in the memory state. QC is still in the memory state. That's good. So in the next clock transition, it retains the same value as before. So that's fine. In the next clock transition, when QC is 1, right? And that means this has to toggle. So by the configuration that we have seen here, this would have toggled if I actually made this configuration. This would have toggled to 1 on the third clock pulse. But we don't want that to happen. We want the toggle to happen on the fourth clock pulse, right? And similar thing would have happened here, right? Here, this would have toggled on the 7th clock pulse. The 1 value would have become 0 on the 7th clock pulse. Okay, so the next suggestion was, so you see that, right? So that's a good suggestion. It could look, it seemed like it would work, but not quite the way we want it to work. Okay. Now the other suggestion was, instead of directly connecting that, we had QD and QC, we added them together, applied it as signal to JB and KB. Would that work? We're taking QB and QC, okay, as an out, and the output of that applied as an input to JB and KB. Now, when that happens, we have to look at both QC and QD, right? Now, QC and QD, when they're both ones, only then the output of the AND gate will be a 1, right? When they're both ones, this is when it happens. When they're both ones. Only then I'm applying a 1 to JB and KB. That means in the next clock transition, the QT plus 1th, I toggle. But before that, it's all configured as memory, right? Because the output of the AND gate will be 0 for all of these values. For all of these QC and QD values, the output of the AND gate is a 0, right? So until this particular stage, I have the memory state. On the 4th clock pulse, because I'm applying a toggle or a value of 1 on my JB and KB value, so on the 4th clock pulse, it toggles. That's exactly what we want. And that's exactly what we should be doing. And you can, again, the next toggle on QB happens here on the 8th clock pulse. No, sorry. Yeah, on the 8th clock pulse. That's correct. Right? That's when it toggles. Was in the memory state. I'm applying a 1 on JB and KB. So on the 7th clock pulse, on the 8th clock pulse, the QT plus 1, it toggles. So that should work. So that's good. So now we got QB as well. What about QA? So now that should be pretty straightforward, hopefully. Absolutely right. So as you can see here, I should toggle on for QA, I should toggle on the 8th clock pulse. That means it should be 0 for 7 clock pulses or 8 clock pulses if I count from 0. And it should toggle on the 8th clock pulse. And I'm applying a 1 if I basically take this and it with QB and apply this as an input to JA and KA. That's exactly what I'm going to get. So I'm applying the toggle pulse on the 7th So on the 8th clock pulse, on QT plus 1, my QA toggles and the behavior continues. So now I have designed a simple synchronous counter. So in this case, I don't have to worry about the delay of the clock, because each of my stage is synchronized with the master clock. So I don't have to worry about the delay of the flip-flop stages itself getting added up. The only delays I have to worry about is the delays of these individual gates, which is going to be significantly less, and they're not going to be added up in this case. So that's a 4-bit counter. You'll still be getting added up, but again, not at the same pace as you would find for the ripple counter. Does that make sense? How to design the synchronous counter? So that's now it's synchronized with the clock. Now, as you can see here, it's not very straightforward to design this. You need to really, think about it. You need to examine the inputs and see how you can configure those each stage to obtain those inputs. So it's not a very trivial thing, especially if you want to design something more complicated with a more complicated count pattern. Okay, because remember that your counter does not have to be counting this way. You can design a random counter as well, or some arbitrary counter that would generate the required timing signal for your case, right? So your counter does not have to be a simple up counter or down counter that counts in a particular sequence, right? All right. So for more advanced counters or more advanced synchronous counters, this approach may not be the most general purpose approach. We need to come up with some better approaches that would allow us to design these kind of systems more easily. Okay. All right. So with that, we concluded the discussion on the counters. Okay. Again, I just want to make comment that these are not the only counters available out there. In fact, in your book, you will have many different examples of different counters, but of course, we can't cover all of them. But hopefully, I gave you some foundational knowledge and counter that would basically allow you to, once you allow you to read through the textbook, understand the operational principle of the other counters that are available out there. All right. So now let's start a new topic. So now we have basically gathered all the fundamental building blocks that we need to come up with a new framework of designing sequential circuits. Okay. Now that particular framework is what is called the state diagram approach or state machine approach, the design of state machines. Okay, so let's talk about state machines. Now, before we actually talk about state machines, what are state machines? Right, as you can see, these are machines that can exist in multiple states. In the simplest example, simplest definition would be a machine that can exist in multiple states. But before we actually look into the design of a state machine, of a digital circuit, right, let's actually understand what a state means, really. What do we understand by this term state? Again, this is nothing new. This word we have been using all through our lives, right? Now, when I refer to the state, I don't, again, this is not referring to the geographical definition of state. Okay. When we apply that onto our own selves, we talk about state of mind, right? State of mind. So, in terms of that, as reference to the state of mind, how would you define a state? Anybody wants to go for that definition, or what do you understand by the state? as human beings, we can think about ourselves as state machines, right? So we are machines that can exist in multiple states. So what do we call those states? What do I mean by those states? Julia, what do you understand by states? Condition, okay. What condition? What kind of a condition? State as a state of being. You can think about state as a state of being, right? Now, everybody of you would be in multiple states of being, right? Or must have experienced multiple states of being through your life, right? And you cycle through those states of beings, right? Now, so with that, let's actually look at state as being an emotional state. So when we again refer to human beings, we think about emotions. We think about the state as a state of being, as an emotional state that I'm in a particular time, at a particular time, okay? And so let's think about states in that particular direction, in that particular manner, all right? Okay, now when we talk about emotions, let's actually explicitly list out the different emotions that we can find ourselves in. We will think about emotions as a state of being. Let's list out different emotions that we experience. So let's see how your class does. Because this is an exercise I do with every class. And I get a surprisingly large list of different emotions that sometimes I never even thought about. So let's see how you guys do. Let's list out some of the more common states of being, and relaxed. Okay. Yeah, let's one state at a time. So let's start with relaxed. That's a state of being. Your mind is relaxed. You don't have these thoughts zipping through your mind. So it's a state of being. It's an emotional state that we would like to be in. Relaxed. Okay. Any others? Anger. Yeah, that's a state of being or an emotional state. Just give you uh, how the other classes compared. I think the maximum we had was 28 different emotional states. 28. Rage, nervous. Okay. Uh, Anger. Okay, rage. Kind of similar, but maybe this is a more angrier version. What was the other one? Nervous. Okay. Nervous state. Grief. Yeah. Yeah, that's something. Yeah, I know. That's true. Yeah, it's. I think the times we are living in, with the COVID and all the things that are happening around, we forgot about the happy state. Yeah, that's something that should be in the beginning, right? Mischievous. Okay, don't mind my spelling here. All right. Mischievous. Prideful. Okay, pride is an emotional state. That's good. Let's see. Confident. Cocky. Again, kind of similar, I guess, but different grades of that. Confident. Okay. Pathetic. Yep. It's good. The list is growing. Jealous. Sympathetic, anxious, yeah, anxious is sympathetic, okay. You're doing very well. You guys confused? Okay, let's see. Petty. Is that an emotional state? If I were to draw let's say if I were to draw an emoji for that, how would you draw that? Empty, drained, or empty? Drained, okay. Or tired? Is that what you're referring to? Tired? Okay. Yeah. Optimistic? That's hopeful. Yeah, that's an emotional state. Disgusted? Mm-hmm. Again, you have different grades of that. Wow, 20 reaching there. Embarrassed? Yep. I would put it. Attentive? That's a good one. All of them are good here. We have to do it here. Attentive. Okay. Good. 21, that's a pretty good number. Growth. You guys really want to beat the record. It looks like smart, bold, smart, or feeling of smart, feeling intelligent, maybe. Feeling smart. Okay, maybe that can be considered an emotional state. Let's see what else we have. Bored or excited. Though again, bored is different from excited. Oh, yeah. Bored. Excited. Did we not have excited? Okay. Good. Frustrated. Okay. All right. So, in fact, there was a CNN study that actually performed a scientific study to examine how many different unique states we have. Enthusiasm, self-destructive, surprised, remorseful. Okay. And that CNN study actually looked into this, and you actually have an expression, a human expression associated with each state. And I think the number of unique states that they came up with was about 26, I believe. Impatient, yeah. I guess impatient is also excited a little bit. Focused is attentive, grumpy, vulnerable, feeling of vulnerable, you're feeling vulnerable. That means, let's see, I can relate that to anything already here. Calm. Calm is relaxed. Yeah, impatient. So that's good. You guys did it really good. So you beat the record. So that's good. So and I'm very impressed with your class. So yeah, I wish we could actually do this in a live session where I could see your faces. Impatient is a bit different than excited. It's more not okay. Impatient. Let me. Again, I'm not able to keep up with the rest of the list, so please excuse me for that. But anyway, I think 28 is a good number. I think I will keep it at this for now. I know you have exceeded that, but let's. So these are pretty good states of emotions that we exist in. So something that we also have to examine, right? As a human being, we went through all of these stages, and most of us, or all of us, at some point in time, must have felt each of these states, right? It's not like we exist in the same state forever. Thankfully, we don't exist in that same state. We move on with time, right? Time is the one that facilitates moving from one state to the next, right? And so basically, we have a sense of time built into our system, uh, and we experience time, and we move forward in time, right? Now, if I want to again closely examine our own behavior, our own experiences, right? Uh, we also know that at a given instance of time. So these are some of the observations. Okay, number one. Again, these are you can think about these as obvious observations because we all experience this. One thing, we don't exist in the same state all the time. We don't exist in the same state. And it's not even possible to do that. Yeah, I mean, even if you're happy at a given instance, you can't just be happy in the same state for the rest of your life, because again, if you want to feel happy, there has to be we need to feel the contrary emotion as well, so that in the next time when the contrary emotion goes away, we can actually appreciate the happiness. Like, that's why, for example, a simple example would be summer and winter, right? Now we have to feel the winter so that we can appreciate the summer. If there was no winter at all, then if it's always summer, it's always, you'll be happy for some time, and then you kind of get used to it. You just yeah, again, that's a more complicated discussion there, Cameron. Yeah, that's true. So yeah, so thankfully we do switch states with time. And the second observation is time. Again, time facilitates the state transitions, right? Facilitates state transitions. What else? What are the other observations? So we don't exist in the same state. At a given instance of time, we only exist in a single state, right? If I take a snapshot uh, of a person, then that person will be basically existing in one state at a given time, right? Even if the person is, let's say, has some kind of a bipolar disorder or something like that, uh, at one instance of time, he would still exist in a single state. Or at a given instance, exist in a single state. Among all of these multiple different states, I exist in a single state. I don't know what state, but I exist in only one state. Okay. What are the other observations? Now, what determines the state I would exist in? What do you think? What would determine the state I would exist in? Or let me put it this way. Let's say I'm in some state. What determines, or what combination of factors would determine my next state, and what state I will be existing in the future or in the next instance? Okay, the conditions before and some event. Okay, so can I say my present state itself? Present state. That means whatever state I am in right now, and and the events. Present state plus, so combination as in plus the current events. Are you able to see it? Yeah. The present state and the current events would determine what my next state should be. What my next equal to next state. Okay. Again, that's from common experience, right? The conditions or the state of being I am in right now, and the events that are occurring, or the inputs. When I say events, that means whatever I'm experiencing through my senses, through my mind, that would determine my future emotional state, right? For example, I'm in a happy state right now, and I get a email saying that I got my next grant, for example, a big grant. I would continue remaining in the same happy state, right? Or, for example, somehow I'm feeling dejected, and I get some congratulatory note from somebody saying that I won something. Then my state of being immediately changes. I go to a new happy state. So I had this state transition. I had just now I had this dejected state, and time as well as, okay, the time facilitated those transitions, but the external events as well as my present state determine what my next state should be, right? So these are the observations. Now I can put down all of those observations that we have listed in the form of what is called a state diagram. Okay, just as a snapshot of if I were to draw a snapshot of what would make you in the most simplest terms. Okay, of course we are complex individuals. It's like, it's not as simple as drawing a state diagram for in a simple representing the entire complex individuality of a person. But if I want to simplify it, if I want to just simplify everything and then put it down as a snapshot in the form of what is called a state diagram, I would do it this way. Okay, something like this. So from the states that we have identified, I would choose 5 of the most important states, or 5 of the states that we associate with most commonly, and then I would use that to draw my timing diagram. Okay, so let's do that. So let's say, the most common states, I'll start with the happy state now. Let's make it more optimistic. Again, that's one of the important states, common states that we are in. Angry state is another one. What else? Sad state. Let's choose 4. Let's choose 2 more. What do you want to choose? Let's say I want to represent the, let's see, disgusted. Okay. Afraid. Okay. Afraid or disgusted. Okay. Disgusted. What else? One more. We'll choose one more, and then we'll draw our diagram. And you guys should let's see, afraid and disgusted. Inside out. Afraid make it inside out. I don't quite get that. Oh, okay. Gotcha. Yeah. That's a good movie. I really like that. The movie. That's, yeah. Okay. Afraid. Okay. All right. So let's do that. So I have 5 emotional states. I want to draw a state diagram for an individual having those states. So let me represent those states by using these emojis. A happy state is pretty simple. I have a smiley face. That's good. Angry state. Uh, how does it look? How does the mouth look for an angry state? No, that doesn't look angry. That, okay. That's your angry state. Sad state. That's easy. Disgusted. I don't know how that will work. Okay. Afraid. I need to recall what the movie, how it's depicted in the movie. Afraid state. Okay, now you made my life a little bit more difficult. Oh yeah, good. Thank you for that suggestion. That's much appreciated. Like that? All right. So, okay, so now I have that. Um, and I would represent the state transition. Again, this is my states of being. So I have 5 different states. Okay. And to represent the state transitions, what I will do is I will go to each state. Let's say I'm in a happy state. Okay. Now, the kind of events would determine what my next state transition should be, right? So in this case, let's say I'm in a happy state, and a happy event would take me back to the same state. So I would basically represent that as going back with this set of arrows, right? Going back to the same state, a happy event. That's of course very relative term, but anyway, so that's something happy, some happy event with for that particular individual would take it back to the same state. Again, when I say these arrows, what are facilitating those transitions is time, right? Because we move forward in time. We are not frozen in time. We move forward in time, and that is represented by these transitions. So time is the one that facilitates, and the events and the present state are the one that determines the next state. Okay, so I'm in this state. A happy event occurs. In the next time instance, I remain in the same state. I go back to the same state. Okay. On the other hand, uh, let's say I'm in again. So if I want to draw the timing diagram in completely, I would need to go to each state, look at all the possible events that can happen on me. Okay, and then draw these similar transition diagrams. Okay. All right. Now, if I'm in this state, happy state, what kind of events would be taking me to the angry state? Actually, this is yeah, okay, that's much better. If I'm in the happy state, what event do you think would be taking me to the angry state? Any suggestions there? And I would represent that using again, you know, these arrows. So what should I write for the event or the input? Or I may not have a direct transition, which is also possible. I may also be transitioning depending on the individual. I may also be transitioning from here to depending on the input. What is this? What was this one? This was the disgusted state, right? Okay. This was afraid. Okay, I may be transitioning in this way. I go to the sad state, afraid state, based on some, let's say, rejection or something like that. Okay, rejection or loss, some kind of a loss. And if that event persists, I may be transitioning this way. And if the event still persists, the same event still persists, I may be transitioning this way. So again, you may not have a direct transition, but you may be transitioning through time if the event persists in time. So you're acting from one state to the next and so on. Okay. And likewise, I will be able to, so likewise, I should be able to complete this timing diagram if I know what kind of events are there to start with, and how these events make me transition from one state to the other. So when I'm trying to decide how the state transitions occur, what I should be doing is I would be going to each state and looking at the different events that are occurring on the state and drawing the corresponding transitions from that state. Once I'm done with a particular state, I would move on to the next state, repeating the same exercise and eventually going through each of my state to completing my state diagram. So once I complete the state diagram, basically that kind of represents as a snapshot of how that particular state machine, in this case, the human being, is expected to operate. Okay. All right. Does that make sense? Any questions here? Now, in the next class, what we are going to do is we'll extend this concept. So we talked about human beings, their emotional states as a state machine. We'll extend that concept to the design of machines, to actual machines that can exist in multiple states. As a matter of fact, you can actually design a robot, assign some states to that, and emotional states to that. You can design a robot that can exhibit all of these emotions based on the inputs you provide to that robot. Okay, so we'll apply the same concepts in the design of actual machines in the next class. So let's stop it here, and let me see if you have any questions so far. So we'll look at the parallels between the human beings as state machines, and if I want to extend the concept to the machines, to actual man-made machines, how would I do that? What are the parallels between that and this? And then we'll look at the design rules for the design and so on in the next class. So with that, let's actually, let's actually stop here recording.